Hi, so welcome to this episode. This is about something that we'll call the 4 panels method. This is a simple approach to presenting information for commanders and decision makers, as you'll see, who need a lot of information very quickly. And it's something we brought together over time with some work from workshops with DSTL and the British Army, among others. So this is one of the scenarios that we had at a workshop. It was a DSTL Public Health England workshop. It was about the impact of an airborne dispersal of an infectious agent across Manchester. And the question was, how do we communicate to a set of commanders who have to make decisions on where to send support staff, health service staff, doctors and medical aid across the city? How do we communicate where the highest impact is and where the most certainty of that impact is? So in this case, the PHE had a supercomputer simulation of the infectious agent which spread across the city, and they ran that 500 times. And from that, you get 500 estimates of where the most impact is, and that gives you an impact estimate and a variation, a variability of that impact estimate, which gives you a model of uncertainty. So the outcome of this particular scenario was a visualization like this, where there were very simple labels for high impact areas in red and an ability to select all the high impact areas in the city. This actually shows all of the areas in the city that were impacted, where there was a non-zero number of casualties in this disaster scenario. There was also an 80-page report which summarised all the information presented at the workshop. So then at a second workshop, we had an attack on a humanitarian aid operation at a seaport. So in red's outlined an area where a troop ship is supplying aid, and there is an intelligence report that there'll be an attack on that area within the next few days. So the question is, which day of the next 3 days is the best day to evacuate? Day 1, 2 or 3? Again, another 500 simulations were run, and they modelled the number of fatalities in each day from each weapon strike. And those fatalities, in this case, because it was a CBR weapon, that was chemical, biological or radiological, it was dependent in part on the weather and the wind speeds. So the day on which it might be best to leave with the least possible casualties would vary depending on the weather, among other things. And the aim here was to advise the commander, based on these simulations, which day would it be best to evacuate. So typically here we have a commander who's deciding on a course of action. Each individual group advising the commander may have no more than 5 minutes to present information. So this, after much discussion, and it's not obvious looking at this whole of the discussion that we had, was the result. So it was a 4-panel report. The first panel just summarised the request. What was it that the statistical and modelling team was asked to do? And in this case, it was to evacuate, model the day of evacuation for the area of operations. This was in a context where only certain things were considered by the simulations, and they're listed here. Wind direction, the altitude the weapon goes off, the particle size and the release mass of the particles, the amount of weapon that was set off. There was no other factors accounted for, and the intent of the adversaries, what they were trying to do, wasn't included. So were they trying to cause casualties? Were they trying to disrupt supply lines? Their strategic intent wasn't considered. It was just looking purely at number of casualties, number of potential fatalities from that weapon release. Then in panel 2 here is a summary of exactly what the advice is here based on the modelling. And based on this modelling advice, which we'll look at in a second, the best days to leave were day 1 and day 3, and day 2 was a much weaker choice. This very short summary is there to give you the most information in the shortest time, so that if you have to take action quickly, just read that and you should know what the results of the simulation mean. Then there's a bit more detail, which breaks down per day what the most dangerous scenario is. So what's the worst case for that day? What was the outcome that was most likely from the most number of simulation outcomes? And that perhaps easier to understand in the graph plot on the right. Now, typically, we were informed that it's not a good idea to give distributions like this to commanders, but in this case, the captains who were working with us said that they could explain this. So the peak of the green bars is where the most likely outcome is. The simulation says the most often that's going to happen. And you'll see on day 1, it has the lowest likelihood of fatalities. The vertical axis is numbers of fatalities. Day 2, the most likely outcome, has the highest number of fatalities, and day 3 is in between day 1 and day 2. But then you also look at the highest risks. What's the worst outcome? So on day 1, the worst outcome is pretty high. Day 2, it's very high. Day 3, it's quite low. So day 2 was almost certainly the worst day to evacuate the port. The worst, most likely outcome and the worst case outcome. The wording of this, most dangerous scenario and most likely outcome, were carefully chosen based on wordings that the British Army tend to use in their briefings already. So here you might well go on day 1 because the most likely outcome is the lowest number of cases, and if you don't go on day 1, you're most likely to wait for day 3. And panel 4 shows some additional information, so it summarises the numbers from the graph above. The most dangerous scenario, the most likely scenario, and then what's going to happen 1% of the time. This many or more fatalities are predicted. So the goal here is to give the information around the decision, the context, the contingencies for the decision, the recommendation, the most likely and most dangerous outcomes, and some supporting information so you can see the evidence behind that. You'll notice there's only one graph in this, and there's quite high reliance on text. And that's often the case in visualizations. You have to know what is worth writing and what is worth drawing. What conveys the best information at the time. If we roll forward to last year, this was summer 2020, when we were looking at modelling the real world situation of COVID-19 impact on universities last September. So this was V-KEMS, which is a group of mathematicians doing the modelling, and I was attached to that to try and summarise some of this in terms of a visual form. So we took a similar 4-panel plot and we applied it to 9 different recommendations from the modelling. You'll see the first panel, again, it's the context for the simulation and for the decision. There are certain assumptions, and quite a lot of assumptions with COVID, that there was an infectious person in the room, that everyone had to do 2 hours in-person teaching per week, that social distancing was set at 2 or 1 metres, and that 1 staff member and between 5 and 32 students were in the space. The primary activity there was not shouting or singing, but was teaching, so it was talking. When it says reckless intent is not included, what that means is that people are not deliberately trying to infect a room. What's happening is that by chance people are turning up in the room with COVID. And then there's a straightforward summary there. We modelled 1 2-hour class, 2 1-hour classes 2 days apart, and 3 40-minute classes 48 hours apart. And assuming there's a range of teaching activity there and a range of social distancing activity, then 1 2-hour class a week was the best option. But then there were other options depending on whether you had low or high density teaching. Then the graphical summary here is what happens with the social distancing. You can either have 44 students or 16 students, depending on the social distancing and what was 164-seat lecture theatre. And from that, you can see there's some really huge constraints on universities last year. If you want to have 2-metre social distancing, you're going to have 10 times less students, and that would imply 10 times the number of lectures. And as a result, most universities started doing teaching online. Underneath that, there's some detailed modelling results, and they're about different levels of talking, either in lectures or active seminars. So a lecture, only one person's talking, so there's a different model applied than if there's a whole room of people talking. And there's different recommendations of what's the best outcome. So there were, as I said, about 9 of these 4-panel summaries, and they went off to universities around the country to try and explain the modelling results to what were really gold command teams in universities trying to decide what to do with it before the upcoming September. And then finally, here is another scenario where we've used this 4-panel structure quite successfully. You may or may not know that every weekend in the Guardian Observer, Anthony Masters and David Spiegelhalter do a short summary of some statistical results. It doesn't come with any graphs or graph plots. And one of the things I did for a number of weeks was do a visual summary of these in this 4-panel form on the right. This one here was is 12 weeks between COVID-19 jabs too long? And there was a question earlier this year about this. What gap is sensible? probably can't see the detail here, but if you look in the graph on the left, what it says is that what you want to try and do is get out more first doses as quickly as possible, rather than get double doses out and leave some people unprotected entirely. And the outcome of that will be fewer deaths. And there are certain things there as well, additional evidence from expert sources in immunology. So there's very often this appetite for visual information and detailed information behind short stories in the press, and rarely do people have time to do this. But it seemed quite successful simply from the number of people who looked at it on the web. So what would I recommend if you're doing this kind of information summary for decision makers? Consider this 4-part structure that we developed with the British Army. On part 1, you're giving a concise description of the question and the context, the scenario, and the contingencies around that question. In part 2, you're giving a very quick summary of the outcome and the recommended courses of action, or the recommended worst cases and most likely cases. And then in panels 3 and 4, you can give a graphical representation of technical information. Very often we've included uncertainty in this because it's important to understand the distribution, sometimes the range of options that are there, and that there's not usually a black and white choice in most decision making. And then finally, panel 4 adds more information, some extra detail, which illuminates some of the other work. The environment in which people make decisions is often important, and this is an environment we have at Newcastle, the Team Decision Theatre in the Catalyst building. This really gives a 360 room where 3 or more teams can take part in decision making exercises. It's got 3 large touchscreens and then a very large 4.7 metre screen at the front of the room, onto which any of the touchscreen contents can be broadcast. And this gives you an ability to set 3 teams off working and then to bring the information back to the middle of the room when they need to see it. So the 4-panel method sets up a set of structured information within a scenario, and you can then bring to commanders or decision makers' attention a whole range of information around context around a particular visualization. Thank you for watching.